Welcome to this lecture 7 of module 2 of the course called Game Theory and Economics. Before we start, let me recapitulate what we have done in the previous lectures. What we have done is that we have defined what is known as a Nash equilibrium, an equilibrium concept used in game theory, and we have tried to solve different exercises just to give you an idea how Nash equilibrium is actually used. We have already defined what is known as a strict Nash equilibrium, where the action profile is such that if someone deviates and tries to take some other action other than the Nash equilibrium action, that person is strictly worse off. And this applies for every player. So these are the preliminary things that we have done. What we shall do today is to introduce another concept of game theory, which is extremely useful in finding what are the Nash equilibria, and this concept is called best response function. The reason for introducing this idea of best response function is that in many cases it may happen that the number of actions that each player can take is quite substantial. It's a large number of actions, and it may even happen that the number of actions is infinite. Suppose I can take any action, I can choose any number between the interval 1 and 2. In that case, the number of actions that I can take is infinity. Now, if that is the case, then it's difficult to use the method that we have used so far to find out the Nash equilibrium. Each and every action profile has to be checked in terms of possible deviation and checking for whether that deviation is profitable or not. If I have infinite number of actions, there will be infinite number of profiles to check. So what do? We basically in those cases use the concept of best response function. So let me try to define what is best response function. Let me try to give an example so that it becomes clear, and this example is from the case of discrete actions. Then we can generalize this and give a general definition. Take the case of battle of sexes, for example. So player 1 has 2 actions, going to boxing match and going to the opera. Player 2 also has 2 actions, going to the boxing match and going to the opera, and the payoffs are 2 1 0 0 0 0 1 2. Now in this case, if player 2 is playing action B, player 1 has 2 actions to choose from, B or O. Now action B for player 1 is giving him 2, while action O is giving him 0. So we say that with respect to action B taken by player 2, action B by player 1 is the best, because by action B he is getting 2. So it is written like this: B for best response, and we add the subscript 1, that is the best response of player 1 with respect to the action of player 2, which is suppose B is B. There are so many B's, it might look a little confusing, but that is how it is. If player 2 plays action B, then the best response for player 1 is playing B, and similarly if player 2 plays O, best response is no longer B, then the best response is O, because from O he is going to get 1. If he plays B, he is going to get 0. So, with respect to action taken by player 2, which is O, his best response is O. For player 2 it will be just similar, because it's a game is more or less a symmetric game. For player 2, if player 1 takes the action B, his best response is B, and if O. So, that is how it is defined. I mean, it is an example, but if I try to give a general definition, then what should it be? It will be that given the actions taken by other player, which action is best for me, that action will be called my best response with respect to those actions taken by other players. So, it is a functional relationship. What I get, the value that I am getting here, it's a set value. It's like the following. Giving me an action which has to be taken. So, this is defined as BI, I for player, any player, I can be 1, 2, 3, etc., etc., and it is defined over A not I. So, A not I is an action profile which gives me those actions taken by other players than I. So, this is the definition of best response function of any player I. It is telling me that best response function of player I with respect to, it is defined over the actions of other players, is an action, or it might be more than one action also, such that given what the other players are playing, which is A not I, this action AI should give player I at least as much as any other action. This any other action is generically given by AI dashed. AI dash can be any action from his action set capital AI. So, this is how it is defined, that given the action set I have, I shall pick that action as my best response, which is giving me the best payoff. Just a few comments. Firstly, it is a set valued function. Which means that it is giving me some action which is to be taken by player I. It is not giving me any number or as such number or any other thing. It is giving me what action the player should take, which gives him the best payoff given what the other players are doing. Now, what was the purpose of defining this best response function? The purpose of defining this best response function is that we want to find out if we can use this idea to find out the Nash equilibrium of any game. And how can that be done? Well, it is the following. I have an important result. Think about this. A star A star is an action profile. It's like A1 star, A2 star, etc., An star. This action profile A star will be a Nash equilibrium if for every player, if for every player I, Ai star belongs to Bi A naught I star. All right. So, which means that given other players are playing A naught I star, Ai star, the action that is the Nash equilibrium action, must belong to the best response function of player I. And this is obvious because if you remember what is the definition of Nash equilibrium, in the Nash equilibrium, given what the actions of the other player, I should be doing my best, and that means that that action must belong to my best response function. It is as simple as that. And the crucial thing is that this should happen for everyone. So, if I have two players, suppose 1 and 2, and I am considering whether A1 star, A2 star is a Nash equilibrium action profile, then it must happen that given A2 star taken by the other player, then the best response for me should be such that it should include A1 star. There might be other actions also, but it should include A1 star. And similarly, this should also happen, that given the action taken by player 1, which is A1 star, the best response function of player 2 should include A2 star. Then we have a sort of mutually reinforcing of actions. Given what you are doing, I am doing my best and playing my action, and given the action, this action taken by me, your action is that action with respect to which I took my best response action. So, this best response function therefore is closely related to the idea of Nash equilibrium. In particular, if it is the case that this best response function includes only a single element, that is, it's a unique valued function, it's a singleton set, in that case the thing becomes more easier. It's the following: suppose B1 2 is B1 so it's a single value, and similarly in that case what I need to solve, it does not have more than one element, that is what I am trying to say. In that case what I need to solve is these two equations. One is A1 is equal to B1 A2 and A2 is equal to B2 A1. If I can solve these two, I will find the Nash equilibrium, all right, because B1 will be a function of A2. So, I have one equation in two variables, and here also B2 is a function of A1. So, another equation in two variables, two equations, two variable. If I solve them, I get the Nash equilibrium. So, that is how it works. Before I tell you how to solve these problems in case of continuous variables, let us look at how this device, this idea of best response functions, can be used if we have discrete actions, like we have been having so far. So take this game and we shall try to see whether we can use the idea of best response functions to find out the Nash equilibrium. So this is the payoff matrix. Suppose we are to find out the Nash equilibrium or Nash equilibria by using the best response function. Then what is done is that first let us try to find out what are the best responses of player 1. Now B1, that means B1 given L is what? B1 given L means if player 2 takes the action L, what is the best action for player 1? Well, it is a single action which is M. So we have a singleton set. If the action of player 2 is C, then his best response is T. If the action of the second player is R, player 1 now has two best responses. One is T and the other is B. Alright. So these are the best responses of player 1. What about player 2? If player 1 takes the action T, his best response is L. If player 1 takes the action M, he has two best responses, L and C. And if player 1 takes the action B, there is a single element R at which he is getting the maximum payoff 2, which is R. So this is how best response functions can be used in this exercise. But what are the Nash equilibria? Well, to find that out, we shall use a very simple technique. If player 2 is playing L, player 1's best response is M, right? Then we put a dot over 2. Why over 2? Because we are considering the best response of 1. That's why I am putting a dot over the payoff of 1, which is 2. If player 2's action is C, his best response is T, so a dot here. If his action is R, there are two best responses, here one, here another. So these take care of the best responses of player 1. Now let us talk about the best response of player 2. If player 1 is playing T, his best response is L, so I have a dot over 2. If M, L and C, if B, only R, Now once I have put all the dots, what are the Nash equilibria? Well, the Nash equilibrium action profile will be that action profile where I have two dots, not a single dot but two dots, and this is happening here and here. So there are two Nash equilibrium in this case. One is ML, the other is BR. Two Nash equilibria are there. Now This was about Nash equilibrium in case we have a payoff matrix and all that. But the same idea of finding the best responses and then try to match the best responses of two players, because what is happening here is that we are trying to match the best responses. If the two best responses are intersecting, they are matching with each other, which is happening at ML and BR, then those action profiles are defined as the Nash equilibrium. The same idea can be done diagrammatically also. How it can be done? Let us take another exercise. So, this is a diagrammatic technique. So, here the game is the following. Now, instead of putting dots here, what we are going to do is to put some dots, but not in this matrix itself. What we are going to do is to draw two axes like x axis and y axis, and we are going to put the actions of player 1 here A1 and actions of player 2 here A2. So, player 1 has three actions TMB, T, M, B, and player 2 I know has three actions as well. They are L, C and R. So, L, C, R. Now, given player 2 is taking action L, what is the best response of player 1? It is M. So, LM, here is LM, I put a circle here. Circle is representing the best response for player 1. So, circle is like B1, A2. If player 2 plays C, then one has one single best response, which is C, which is T. So, CT, I put another circle here. And if player 2 is playing R, player 1 has all the three are best responses. So, TR, MR and BR. Now, let us think about player 1, sorry player 2 and player 2's best responses will be given by dots in this diagram. Now, if player 1 is taking the action T, player 2's best response is C. So, TC, here I put a dot, and this dot, since there is a circle already there, I put the dot inside the circle. If player 1's action is M, player 2's best response is L. So, ML is another ML. And finally, if player 1's action is B, all three L, C, R are best responses for player 2. So, BL, BC, BR, BL, BC, BR. Now, as one can guess from the exercise that we have done just now through the matrix, that is this one. One can guess the Nash equilibria will be those action profiles where I have the dot as well as the circle. So, there will be 3 Nash equilibria here, one is here, the other is here, and the third one is here. So, the Nash equilibrium will be called the Nash equilibria. 3 Nash equilibria are there, one is ML, then we have TC, and we have PR. This can be checked from the matrices. Suppose ML, I am considering this one. Now, obviously, player 1 deviates, he cannot be better off. He can either get 2 or get 1, which are less than 3. What about player 2? If he deviates, he gets 0 and 0. Again, they are worse. They are worse than 0. They are worse than 1. Then we have TC. From this, if player 1 deviates, he gets 0, which is less than 1. If player 2 deviates, he gets either 2 or 1, which is less than 3. And BR, similar to the logic provided before, if player 1 deviates, he gets 0, which is not better than 0, which player 1 is getting here. And if similarly for player 2, if player 2 deviates, he gets 0, which is not more than what he is getting in the Nash equilibrium. So, these 3 are the Nash equilibria. Now, these were the cases where we had discrete actions of each player, and we have seen that we can find out the Nash equilibria in these games by using either of these two techniques, either directly using the payoff matrix or by using a diagram, which is a representation of the payoff matrix itself. Now, if it so happens that the number of actions is they are not discrete, but they are continuous variables, then what happens? Then can this method of can this idea of best response functions be used profitably? And the answer is yes. Let us take a case. This game is called Synergic relationship game. And the idea is the following, that I have 2 players. So, players, and the actions that they can take, so let us call A1 is the action of first player and A2 is the action of the second player. They can be any number between infinity and 0. So, any positive non-negative number is allowed as an action. What about the payoffs? It is represented by the following. For player I, the payoff that player I gets is a variable of 2. It is a function of 2 variables, A1 and A2, and it is given by AI C plus AJ minus AI, where AI is his effort level. Here AI and A2, A1 and A2 are the actions which represent the effort level put in by each player. Effort level for what? Well, this is a relationship. The story is that 2 players are involved in a relationship. If I put more effort, given the effort level of the other player, I should get more benefit out of the relationship. It helps me also, it gives me more satisfaction. But if the effort level put in by the other player is constant, it is not changing, it is not increasing, then if I go on putting more and more effort, after a point of time the benefit that I get goes on declining, because if the other person is not contributing, I do not feel very happy about it. So that is represented by this payoff function. Initially given C and given Aj, if Ai rises, then this Ui also rises, because suppose Ai is less than C plus Aj divided by 2. Oh, I forgot to mention C is positive. C is a positive constant, it is a given from outside. Now, if Ai is less, obviously if Ai rises, the whole Ui rises. So, here I have a game theoretic situation where the actions taken by each player could be a continuous variable, Ai and Aj. In particular, I am going to consider two players only, 1 and 2. So, the payoff functions will look like the following. This is how the payoff functions look. Question is, what is the Nash equilibrium here? Now, we are going to use the technique of best response functions, because as you can see, you cannot draw a payoff matrix for this game, because the number of actions is infinite. Now, what was the definition of best response function? Given the action of the other player, I should pick up that action or those actions which is maximizing my payoff. So, in other words, what I should do to find out the best response function is that I should maximize Ui, say U1, with respect to U1. I should find out that value of A1. I should find out that value of A1 which maximizes U1 given the value of A2, and that will be my best response to A2. So, this translates into maximizing A1 C plus A2 minus A1. This I have to maximize subject to with respect to A1. Now, this is a very common problem in differential calculus. If I want to maximize a function with respect to a variable, what I do is I have to satisfy what is known as the first order condition, which is that the derivative of this function with respect to A1 has to be equal to 0. This is the first order condition. Now, let us see if it is what do I get out of this condition here. It will be C plus A2 minus A1 plus A1 multiplied by minus 1 is equal to 0. It is a product of two functions, A1 and C plus A2 minus A1. So, it will be by the product rule, it will be C plus A2 minus A1 multiplied by the derivative of A1 with respect to A1, which is 1, plus A1 multiplied by the derivative of C plus A2 minus A1 with respect to A1, which is minus 1. And if I simplify this, what do I get? C plus A2 minus 2A1 is equal to 0, which means that A1 is equal to C plus A2 divided by 2. This is first equation. Now, notice if I am maximizing a function with respect to a variable, it is this is a necessary condition, this is the first order condition, but there is a second order condition which is the sufficient condition, which says that this should also be satisfied. This should also be satisfied, and which is satisfied here because what is the left hand side? The left hand side is minus 2 and which is less than 0. So, the second order condition is satisfied. Which means that this is indeed the best response function for player 1. And what does it say? It says that given the changing value of A2, A1 should vary according to relationship 1, according to this this function 1, best response function 1. And if I want to draw this in a diagram, how does it look? Now, A1, this 1 can be simplified as A2 is equal to minus C plus 2 A1, which means it has a slope of 2 and an intercept of minus C. In particular, if A1 is 0, A2 is minus C. If A2 is 0, A1 is C divided by 2. Suppose this is C and this is C divided by 2. Suppose this is again C. So, this curve will, this line, this is not a curve, this is a straight line and this should look like this one. It has a steep slope, of 2 and an x intercept of that is horizontal intercept of C divided by 2. Okay. Now, let us concentrate on the other best response function. Now, before concentrating on the other best response function, let us see what it means, what it shows, this best response function of player 1. It shows for each value of A2, if I take any value of A2, suppose this arbitrary value, I find that value of A1 which is the best response for player 1. So, if I take this value, I draw a perpendicular on this line, from the intersection point I draw another perpendicular, and this point should give me the best response of player 1 with respect to this action of player 2. So, this is how this function is, this line is interpreted. For each value of A2, this line gives me the best response of player 1. What about player 2? Remember, U2 is U2 looks like this is U2, and so I have to maximize this with respect to A2, alright, and if I do so, again I will have a first order condition, I will have a second order condition, but the exercise will be exactly the similar that we have done before. And if it is exactly the similar, then the function that I am going to get, the best response function for player 2, it will look like the following. This is how it should look, because for player 1 the best response function was A1 is equal to C plus A2 divided by 2. For player 2 it will be C plus A1 divided by 2. Now, if I want to plot this line, how will it look? We just remove these lines so that it becomes more clear. Now, this line, if A1 is 0, A2 is C divided by 2. So, this is C divided by 2, and this line passes through this point. And what is the slope? Slope is half. So, it will be a flat line like this. This is the best response of player 2. And the interpretation is just like the interpretation before. It is telling me what is the best response of player 2 given any action of player 1. So, I have to read from here, given any action of player 1, suppose this is the action of player 1, A1, I am going up to the line of B2, and from that I draw a perpendicular on the A2 axis. So, this is the best response of player 2 with respect to this action of player 1. So, this is how it is read. Question is, which is the Nash equilibrium? And the answer is very simple. Nash equilibrium is that point where these two lines are intersecting with each other. Since both these lines are straight lines, there will be a unique point of intersection, because these lines are not parallel. So, it means there will be only one point in which they will intersect, and that point is here. Let us call this point M, and you can figure out intuitively, at least from the diagram, that this point has the coordinate CC. This can be verified by solving 1 and 2 also. So, if I solve these two equations, A1 is equal to C plus A2 divided by 2, and A2 is equal to C plus A1 divided by 2. If I solve them together, I should get the same solution, because let me just verify. A1 is equal to C divided by 2 plus half A2, and in place of A2 I can write this. So, now if I multiply both sides by 4, sorry, so A1 is equal to C, and from 2 we get A2 is equal to C plus C divided by 2, which is equal to C. So, indeed from the diagram itself, what we have seen, the intersection point is CC, and that is also can be obtained by solving these two equations 1 and 2. Now, why is this point being called Nash equilibrium? Because of the thing that we have said before, that remember this is what we have said before. If I have two players, and if it so happens that there is one point at which the best response function is giving me a unique point, then I have this unique point as B1, and B1 is a function of A2, B2 is a function of A1. I solve them, I get a unique equilibrium, Nash equilibrium. And if I look at the diagram also, the same thing is verified. Here from C2, so from C, if C is the action taken by player 2, what is the best response for player 1? I go here and I reach here, this is the point C by the horizontal axis. So, with respect to the action C by player 2, C by player 1 is the best response. Similarly, from here if I go up, I reach B2, this line, B2 line, and from B2 I read out that this is again coming back to the same point C. So, going from the same point and we come back to the same point, and that is why this is a Nash equilibrium. Okay. Now, this was the case where the best response functions were linear, there were straight lines. In general, best response functions are not straight lines, it can be curves, and if they are curves, then it is not necessary that the points of intersection is just there is a single point of intersection. There can be more than one point of intersection, and if there are more than one point of intersections, then obviously the number of Nash equilibria will be more than one. So, that is how it is solved. So, before we end this lecture, let me just take you through what we have done in this lecture. Basically, we have introduced the concept of best response functions and how to find out Nash equilibrium from best response functions. We have studied two exercises for in the case of continuous variables, and we have also shown how in case of discrete actions the idea of best response functions can be used to find out the Nash equilibrium. Thank you. First, define best response functions. So, best response function a best response function is defined for a particular player. It is defined as so this is the a notational definition of best response function of player I, written as Bi. Now, this is a function of A naught I. A naught I is the vector of actions of other players. So, best response function of a particular player is defined over the list of actions of other players A naught I, and it is a set valued function. Okay. It gives us a set of actions of player I which are best given player I's payoff function and given what the other players, what actions the other players are taking. So, that is how the best response function is defined. In particular, the best response function could be null valued, which means there is no unique or even more than one best responses to other players action, or it could be a function which specifies more than one action which are best given what the other actions are. Let us go to the second question. How are best response functions used to define Nash equilibrium. This is the relationship we want to prove. So we say that A star is Nash equilibrium Remember, A star is a vector of actions. It's like A1 star, A2 star, etc., An star. So this vector of actions is a Nash equilibrium if and only if every player's action that is generically AI star is a best response to the other players' actions. So symbolically this can be written as AI star belongs to the best response function of player I, and this is true for all I. Okay. So this is how this best response function is relating to the concept of Nash equilibrium, that in the Nash equilibrium every player's action should be belonging to his or her best response functions, and this should be true for every player. The third question: use best response functions to define to find the Nash equilibrium of the Battle of Sexes game. So if you remember the Battle of Sexes game, it looks like the following. This is the wife, this is the husband, and there are two actions here. And these are the payoffs. Now we can easily see that the best response function of the husband, given the wife is going to the boxing match, is to go to the boxing match, and the best response function of the wife, given that the husband is going to the boxing match, is also going to the boxing match. So by using the definition with the relationship that we have just described, BB is a Nash equilibrium. Similarly, OO is a Nash equilibrium, because given the wife is going to the opera, the husband will go to the opera, that is his best response, and given that the husband is going to the opera, wife will go to the opera. So these are the two Nash equilibrium.